Explain about the star cluster. Let me share my screen. Here you see, this is a globular cluster, and this is the core of the star cluster, globular cluster, and you see the diagram of that, the HR diagram or Hertzsprung-Russell diagram of this globular cluster. And you see from the globular cluster, the spectral time is start from around G spectral type, and you see they are old, and you see the turn-off point and red giants, blue straggler, white dwarfs, and red dwarfs, and you see that the temperature is around 6,000, and also the luminosity. And the one is the luminosity of sun, and here the less, and here the up. And this is shows for NGC 104, and you see that it's an old cluster, which its metallicity is minus 0.76x, and it has 12 gigayears old, and its distance is 4,500, and the diameter is 31 minutes. For introduction, we can say what we are dealing with. Faint and globular clusters are faint and normally red. It has red stars, very crowded fields, especially the cores are very hard to resolve. Large telescopes are needed for the core regions. Good spatial resolution is needed. Excellent overview article about the globular cluster you can see from this website, ADS, and globular cluster, galactic globular cluster database are also from this website. You can search about them. How many globular clusters are discovered? You see, the discovery of them is continued, that still new ones are discovered. As you see, the time is 2018. And 157 objects discovered. And you see here, it is here, it's a globular cluster, and you see it is very difficult to detect the globular cluster. Maybe at first you see that maybe there are binary stars, but after a while and analysis, you see that no, they are globular clusters. And here also, it is the core of the globular cluster. You see in different regions with different filters and telescopes. And only a few stars resolved. You see cluster region and background. And we can say also in here, we can say that in open clusters, we can resolve the core easily. But for globular cluster, no, it's not easy to resolve the core. And more globular clusters are in the galactic bulge, and also then in galactic halo, as you see. And we can see that open clusters move up and down of galactic disk, and globular clusters cross the galactic disk. As you see, they cross the galactic disk and pass it. And here you see that the most of them are in galactic bulge. Here you see they're faint. It's a diagram of the this globular cluster. And you see the core, which is crowded and faint. And what is the definition? Core radius, distance at which the apparent surface luminosity has dropped by half. Half-light radius, distance from the core within which half the total luminosity from the cluster is received. Half mass radius, the radius from the core that contains half the total mass. Tidal radius, distance from the center at which the external gravitation of the galaxy has more influence over the stars in the cluster than does the cluster itself. And density profile or King profile. Heuristic description of the density law of star clusters, open globular clusters by Ivan King. And you see its formula. In this formula, F is the stars per square unit or surface density. F1 is constant and RT is radius, FAR is 0. For general formula, you see this one, which K is constant and RC is core radius. And typical globular clusters has RT over RC is approximately 30. Unit for K is V is 10 magnitude per square or minute. The parameters RT and RC can be treated within numerical simulations and can be converted into an astrophysical quantity, for example, RT like this, as you see, and R is distance from the galactic center, M is mass of the globular cluster, and mg is mass of the Milky Way. You see the calculation of the parameters in King profile, also here. And they are all, you see, 19 and 68, but they are not much different until now. And in Gaia data release 2, you see in the left part, you see the proper motion distribution of stars in our NGC 1904 sample colored with the computed membership probability. The sample shown has already been cleaned using color magnitude diagram, isochrone cuts, and parallax selections. The blue marker indicates the peak of the globular cluster proper motion distribution, while the red marker indicates the peak of the background distribution. A counter is drawn for membership probability of 0.9 for reference. You see that core is not resolved, but still very good converge. 82 globular clusters analyzed. You see here for King profile, Gaia will never give any results for the cores. Additional observations needed for Gaia. But for literature, you see they are square, red square, and final samples are green, and Gaia is triangle. Examples of different shapes, as you see, for 2 NGC. Also, it works for open clusters, you see. Motions of star clusters position in galactic coordinates, position the Milky Way or XYZ distance from the sun needed. Radial velocity, proper motion model for the gravitational potential of the Milky Way includes a spherical bulge disk and a spherical dark matter halo. And this is the reference. Here we have a different motion of globular clusters, and we can say most of the globular clusters are symmetry because they survive from the influence of gravitational pull or the differential rotation of Milky Way. Also, you see here, you see some symmetry, and the shapes are more like each other than open clusters, which you see they are different. They have different shapes. So in open clusters, they do not survive from the influence of gravitational pull or the differential rotation. So their shapes are different. And ellipticity, in this figure, you see the ellipticity distribution of globular clusters in the galaxy dashed line from Gaia, from data in white and shown. And you see A and B are the semi-major and semi-minor axes of the ellipse. And you see here the globular clusters, globulars in the galactic bulge are misaligned due to the gravity of the galactic center and direction of the white arrows, as you see. And for here we can say that electricity has no correlation with the age or absolute magnitude of the globular clusters. Electricity has only correlation with the position of the globular clusters. If it is more closer to the galactic center, there is more electricity. For formation of globular clusters, we can say globular clusters also form from one giant molecular clouds or GMC with first or initial starburst. Here is it is a giant molecular clouds. It collapse or with shock waves. There is some globular cluster in the center of them, and then we can say with first initial starburst, globular clusters formed in galactic bulge here, and then we have here fragments in the shell, and then with second starburst, globular clusters formed in the galactic halo, as you see. For further formation of fragments, globular clusters are here, galactic halo. We can see that globular clusters in the galactic bulge are older than globular clusters in the galactic halo. And here it's formation of globular clusters in the outer halo region of the galaxy. Formation of globular clusters has its origin of the system of globular clusters in the Milky Way, and you see there are some words like likely or possibly. So we can say maybe a possible interpretation is the results are inconclusive because of likely or possibly. They are not certain. Two external populations, a halo population, spherical around the center of the Milky Way, very extended in halo. The metallicity is among minus 2.5 and minus 1 dex. The age is between 10 and 15 gigayears. And the other is disk population or bulge, more concentrated around the center of the Milky Way. The metallicity is between minus 0.5 until plus 0.5 dex. And then the age is about 10 gigayears and continuous transitions. see two populations of globular clusters for 153 globular clusters. And you see here the reddening, although the large distance, they have large distance, no reddening in halo, and the new globulars with large reddening and large distance detected. Multiple internal population, multiple main AGB or asymptotic giant branch and HB or horizontal branches sequences within one globular were found, not for all globulars, although same observational quality. No clear morphology detected yet. Also indications of the oldest open clusters. You see here for internal populations, there are some links that you can go through them. Here you see the different helium content or Y here can explain the multiple main sequence. As you see here, different isochrones, and then we have different main sequence. There are some open questions like how can we produce such helium abundances? And for example, here, as you see, we have different helium. And so if we have a part of these diagrams, we see different range of stars have different helium and different populations or age intrinsic of the star clusters, which means are they formed within the cluster? Merging process, what about the merging process? Only in globular clusters or depending on metallicity? What about the metallicity? And here you see the main sequence of globular cluster, but there are two horizontal branch stars, and we can see different range of A's are distributed in different places of globular clusters, and in globular clusters there is double subgiant stars, but one main sequence stars. Also, you see here no correlation with the position within the cluster, and the R is the radius from the center. And also here you see the Omega Centauri observations that fit different isochrones very well. As you see, notice different Z and hydrogen values. As you see here, you see we have different kinds of hydrogen helium. Still, scientists do not know why. And there are different kinds of helium in the globular clusters, as you see here. Thank you for your attention and see you next time. Bye.